Welcome back, everyone. A new type of engine is making its way into the global energy market, promising to reshape how power is generated and used. Known as plasma ignition engines, these systems use superheated ionized gas to initiate combustion more efficiently than traditional spark-based ignition. By creating a stable plasma field inside the combustion chamber, the engine achieves faster ignition, more complete fuel burn, and significantly lower emissions. Initial versions are being adapted for use in both stationary power generators and high-performance transport systems. Early test results suggest a substantial increase in thermal efficiency and reduced maintenance needs due to fewer moving parts and less mechanical stress. With prototypes already being demonstrated by aerospace and energy firms, plasma ignition engines are poised to enter pilot programs in industrial settings and remote energy grids. As commercial readiness improves, this technology may offer a cleaner and more adaptable alternative to current internal combustion systems. Plasma ignition engines work by replacing traditional spark plugs with a high-energy plasma field that initiates combustion through ionization rather than mechanical sparking. This plasma is generated using a rapid electrical discharge that creates a channel of highly energized gas inside the combustion chamber. Unlike a single-point spark, plasma ignition forms a broader area of ignition, allowing for more complete and uniform fuel combustion. This means that fuel molecules ignite faster and more simultaneously across the chamber. As a result, the engine burns fuel more efficiently, producing greater energy output per unit of fuel and generating fewer emissions. The system is also less prone to misfiring under high pressure or lean fuel conditions, which makes it especially suitable for advanced energy systems and future engine platforms that demand both power and reliability. The core component of a plasma ignition engine is its ignition unit, which includes a power supply, a control module, and an electrode assembly. The power supply charges a capacitor bank to a precise voltage level, while the control module determines the timing and strength of each ignition pulse. When activated, the energy is discharged into the combustion chamber via electrodes, forming a plasma arc. This arc ionizes the fuel-air mixture, creating a path for the flame front to travel rapidly and completely through the cylinder. Because the system operates under controlled electrical impulses, the timing can be fine-tuned far beyond the capabilities of traditional spark systems. This allows for optimization based on fuel type, temperature, engine load, and environmental conditions, enabling highly efficient operation in a wide range of scenarios. Another advantage of plasma ignition is that it allows engines to run effectively on leaner fuel mixtures. In traditional internal combustion systems, attempting to burn a low fuel-to-air ratio can result in incomplete combustion or engine knock. Plasma ignition generates sufficient energy to ignite even highly diluted mixtures, improving fuel economy and reducing harmful nitrogen oxide emissions. This is particularly beneficial for engines running on alternative fuels, such as hydrogen, ammonia, or synthetic hydrocarbons, which require precise ignition control. In addition, lean burn operation leads to lower combustion temperatures, which extends the life of engine components and reduces heat-related mechanical wear. The improved stability and adaptability of plasma ignition systems make them ideal for future engines operating under variable load conditions. Fuel flexibility is a key feature of plasma ignition technology. Because the ignition system can be finely adjusted, it can accommodate a variety of fuels without requiring major hardware changes. This makes it suitable for mixed fuel operations, such as diesel-ethanol blends or synthetic methane produced from captured carbon dioxide. The plasma ignition system can detect changes in fuel composition through onboard sensors and automatically recalibrate the ignition pulse characteristics to ensure optimal combustion. This adaptability not only simplifies fuel logistics, but also enhances the potential for using renewable or locally sourced fuels in distributed energy systems. It opens the door to modular power units that can function reliably across regions with different fuel availability and quality. The integration of plasma ignition into power generation systems requires careful attention to thermal and electrical design. The plasma field generates intense localized heat that must be managed to avoid damaging surrounding components. Engineers use high-temperature ceramic insulators, thermal shielding, and advanced cooling pathways to protect the electrodes and adjacent materials. Additionally, the electrical control systems must handle high-voltage discharges repeatedly without signal degradation or arc misfiring. Modern microcontrollers and insulated gate transistors are used to ensure that the plasma discharge is both precise and consistent. These components work together to maintain ignition timing accuracy and system longevity, even during prolonged use in remote or demanding environments. In larger generators and energy systems, plasma ignition units can be synchronized with digital control platforms for real-time performance monitoring and adaptive regulation. Sensors placed throughout the engine collect data on pressure, temperature, fuel composition, and exhaust gas content. This information is fed into a central controller that adjusts ignition parameters on the fly, optimizing each combustion cycle for efficiency and emissions. These smart controls enable the engine to respond to changing load demands or environmental factors without human intervention. For example, in a microgrid setting, the plasma ignition system could modulate fuel use during low demand periods and ramp up power generation when consumption spikes, all while maintaining clean combustion and fuel savings. Durability and reduced maintenance are other benefits of plasma ignition systems. Traditional spark plugs degrade over time due to electrode erosion and carbon buildup, requiring regular replacement. In contrast, plasma ignition units have fewer moving parts and use more robust materials that are less affected by wear. The absence of mechanical contact during ignition means there is less physical stress on the components. Additionally, because the combustion process is more complete and produces fewer carbon deposits, engine cleanliness is improved, and the need for cleaning or overhaul is reduced. This translates into lower operational costs and longer intervals between servicing, which is crucial for installations in isolated or hard-to-reach locations. Scalability is another strength of plasma ignition engines. The technology can be miniaturized for use in small portable power units or expanded to serve large-scale industrial generators. Engineers are currently developing modular ignition units that can be inserted into different engine types with minimal customization. This standardization helps reduce production costs and accelerates adoption across multiple industries. Furthermore, plasma ignition can be integrated into hybrid systems, where conventional engines are paired with battery storage or renewable input. In such configurations, the plasma ignition system ensures that the engine operates efficiently when called upon, complementing intermittent energy sources like solar or wind with stable and responsive backup power. Safety and system diagnostics are built into the design of modern plasma ignition systems. Real-time monitoring ensures that voltage levels, discharge durations, and combustion conditions remain within safe parameters. If irregularities are detected, the system can initiate shutdown procedures or switch to backup ignition modes to prevent equipment damage. Built-in diagnostic tools also allow operators to identify wear, misalignment, or contamination before they cause system failure. Remote monitoring features can be added, allowing technicians to oversee multiple plasma ignition units across a distributed network from a central control center. This remote capability enhances operational reliability and makes the technology more attractive for mission-critical energy applications. If plasma ignition engines meet performance expectations at scale, they could become a foundational component in the transition to cleaner and more flexible power systems. Future designs may incorporate hybrid functionality, using plasma ignition with biofuels or synthetic fuels produced from captured carbon. These engines could serve as efficient backup systems for intermittent renewable sources like wind and solar, or operate in mobile energy units for disaster relief and off-grid operations. In the longer term, adaptations of this technology might play a role in extraterrestrial power systems where traditional ignition methods are impractical. By reducing fuel waste and lowering pollutant output, plasma ignition engines could help bridge the gap between fossil dependence and a cleaner energy landscape. Thank you very much for watching. Please like and subscribe.